Welcome to this video course on power in a data center as it relates to data center racks. As we'll illustrate in another video, the power that enters a data center is usually three-phase alternating current power, which is more commonly referred to as three-phase AC power. It's important to understand how alternating current works to be able to appreciate the fact that three-phase power is actually three lines that are 120 degrees apart. This concept confuses a lot of people, so to have that last sentence make sense, let's start with how current moves in single-phase power. Here in the top picture we have a magnet. The north pole is the positively charged pole, and the south pole is the negatively charged pole. And next to that magnet we have a copper cable. Copper is used because it has an electron that's easily moved. I'm not going to get into basic chemistry 101 that talks about nucleus and electrons and how they function. Let me just state at a simple level that it takes very little force to move an electron away from a nucleus in a copper atom. That's why copper makes an excellent conductor for electrical power. With magnetic forces, positives and negatives attract. If you have two magnets and hold the positive ends close together and let the magnets go, they would push away from each other. If you held a positive and a negative close together, they would attract each other. Electrons are negatively charged. Therefore, they're attracted towards the positive part of the magnet and repelled by the negative part of the magnet. When we position a magnet close to a copper wire or copper coil, the magnetic force is strong enough to be able to start moving the copper electrons. The electron closest to the positive pole of the magnet wants to edge even closer, and the one next to it wants to fill the void that the first one just left, and the one after that fills the next void, and a chain reaction starts in the copper wire. In this simplified example, I'm only showing one end of the copper instead of a loop. There are millions of these electrons in a piece of copper wire. As the electrons move, they generate current. Thicker wire will have more copper, which means it will have more electrons generating current. If the positively charged part of the magnet is directly next to the copper cable, the electrons will be moving towards the magnet at their maximum speed. The alternate part is if the negatively charged part of the magnet is directly next to the copper cable, the electrons will be moving away from the magnet at their maximum speed. Now let's take that magnet and start rotating it clockwise. The magnet is perpendicular to the wire. Note that both the negative and positive poles of the magnet are at equal distance to the copper wire. The attracting power of the positive pole is cancelled out by the repelling power of the negative pole. This means electrons aren't moving, so no current is being generated. Current is expressed as amperes or amps, so the amps being generated here are zero. If we further rotate the magnet another 90 degrees, we have the south pole of the magnet next to the wire. This negatively charged section of the magnet is now repelling the electrons, and they are moving in the opposite direction away from the magnet. The force of the electrons going from one copper atom to another, either towards a positive charge or away from a negative charge, is what causes current. Alternating current is the current flowing from one direction, reaching a peak force, decelerating until it stops, and then reversing direction until it reaches another peak force, at which time it slows down and again stops. One complete cycle is from zero to maximum positive, back to zero, to maximum negative, and again back to zero. That's called a hertz. In North America we have 60 hertz per second, and most of the rest of the world uses 50 hertz per second. A lot of people see the pluses and minuses like plus 2.3 amps and minus 2.3 amps, and they get confused and think that one offsets the other. It doesn't. The positive and negative numbers are used to show the movement of the current. Current is caused by the movement of the electrons, and it doesn't matter which direction the electrons are moving. Here's a simple analogy. Think about leaving your house, getting in your car, and driving down the block. The car starts from zero and accelerates to 30 miles or 30 kilometers per hour. You know there's a stop sign at the end of the block, so you start to slow down and eventually stop. Now let's assume you forgot something at home and decide to back up the same distance you just traveled. You accelerate to 30 again, and then start to slow down as you near your house until you stop. Did you just travel zero distance? Of course not. You traveled double the length of the block you live on, even though you're now back at your starting point. You just alternated directions that you traveled. In our car example, you're moving forwards and backwards, but with copper wire, the electrons move to positive and away from negative magnetic forces. By spinning the magnet, we cause the direction of that movement to go backwards and forwards. But calling it backwards and forwards current doesn't sound right, so we just call it alternating current. An ammeter measures the amps or current in a line. Some will show positive and negative values and others won't. Another method of measuring current is to use a digital oscilloscope. Many charts will show positive and negative numbers to reflect the direction of the current. Remember, plus 2.3 amps provides the same current strength as minus 2.3 amps. Let me repeat this critical statement. Current is caused by the movement of the electrons, and it doesn't matter which directions the electrons are moving. While the above examples of spinning a magnet are correct and Niagara Falls in the US generates electricity this way, other electrical utilities use the same principle but generate current by spinning a copper coil inside of a magnetic field. As the coil spins, electrons move back and forth. The picture shows a simple hand crank, but utility companies use an outside power source such as steam from coal or gas-fired plants to cause the electrical coil to spin inside of a magnetic field. One final note is that since Ben Franklin's experiments with electricity, the commonly used statement about current is that it is said to flow in the opposite direction of the electrons.